This is Absorbance and Fluorescence with Lily Bacon, Nicole Cuba, and Corey Grassmeyer for Group 5A. Our main goal for this experiment was to understand both absorption and emission graphs, and to determine what dye we were using by analyzing the absorbance. There are a multitude of varying factors that contribute to the absorption and fluorescence, including light intensity and wavelength. And from this experiment, we established that energy is not conserved, and we determined that the dye that we were using was lattice dye with a concentration of 1.72 molar. And we determined that the fluorescence was fluorescein. The materials used for this experiment included a mag flashlight, a spectrometer, a fluorescent dye in a cuvette, and an unknown dye in a cuvette. Our experimental process consisted of the following steps. We shined a concentrated beam of light into the dye. We then set up the spectrometer next to the cuvette of dye, and then we determined the absorption or fluorescence of that graph of the dye based on the absorption of the spectrometer. And once we had our data was recorded, we determined the fluorescence and absorptions of the dye based on the wavelength absorbed by the spectrometer.
To find the absorption of the unknown dye, we first had to find the light absorption spectra. So to do that, we hooked a spectrophotometer up to a computer, and we shined a flashlight into the unknown dye and used the spectrophotometer to determine the light absorption spectrum. We did the same thing for the fluorescein, but we had to do it a little differently. It had to be at a 90-degree angle so that the spectrophotometer does not absorb light from the flashlight, and it had to be a very dark environment so that extra light cannot be absorbed by the spectrophotometer, only the light from the fluorescein. For the orange cuvette, we used the equation absorption is equal to the log of the initial intensity over the intensity of the orange cuvette, with the initial intensity being water in a cuvette. And we found that the peak wavelength of the orange dye was about 520, which was the closest to the Lapidus dye. By using the equation, absorption is equal to E wavelength C times L, with L being the path length of 1 centimeter. We were able to make that to find the concentration for the equation to be concentration is equal to A, or absorption, over E lambda times L. And E lambda was 43,000 meters to the negative first. And so we divided by 0.7, which was the peak absorption, to get 1.72, which is closest to the Lapidus dye concentration. For the fluorescent, we did the same thing with the spectrophotometer to replicate the graph of the absorption versus intensity of light. And by doing that, we took the data from Excel and used it to make the graph, and the intensity was scaled by 50 to fit the graph.
And then for why does a certain wavelength enter the fluorescent tube and a different wavelength is emitted when it fluoresces? Light goes into the tube and photons are excited from the fluorescein, and that wavelength is then emitted instead of the wavelength of the flashlight. Was energy conserved? And we said no, because the wavelength goes from covering all light to only green light. And then fluorescein may have been, when we were testing the fluorescein, other light may have been detected from laptops or phones, and the placement of the spectrometer may have not read light appropriately the same each time. And lights were not dimmed completely, and the light from other groups cannot be avoided. In conclusion, we said that our dye was lattice dye based off of the absorption found from absorption equals I naught over I, and the concentration was 1.72 moles based off the equation absorption equals E lambda times C times L. And the absorption of our graphs are the plots of the intensity of the light not absorbed by the dye, and which can be used to find the unknown concentrations of dyes, and fluorescent graphs are the plots of wavelengths emitted by the fluorescence, which makes it different from absorption graphs.